So we've done the aldol condensation for either an aldehyde or a ketone when there's just one type of carbonyl present. What happens when there's two different carbonyl compounds in the same consider what would happen if I took a mixture of propanol and 2-methylpropanol. Reacted this with sodium hydroxide. It's actually fairly common to run these reactions without the solvent if you are starting materials or liquids by just taking powdered sodium hydroxide and adding to the mixture of carbonyl compounds. That's in fact what you're going to be doing in the lab when you do this aldol condensation for yourself. There are alpha hydrogens on both of these carbonyl compounds. So logically, we form enolates from people. And this is the equilibrium reaction. So we will have in solution the enolate that came from our propanol and but we also still have the two different carbonyl compounds present. So you'll see that there are actually 4 possible ways for the two enolates to react with 2 carbonyl compounds. The enolate from 2-propanol can react with another molecule, 2-propanol, but the enolate from 2-propanol could also react with the 2-methylpropanol. And similarly, the enolate from methylpropanol can react with itself, but the enolate from the 2-methylpropanol would also be free to interact with propanol. So there are 4 possible donor-acceptor pairs. Where we have in 2 cases the donor in the acceptor molecule coming from the same species. We call the propanol A and the 2-methylpropanol B, and the donor of the acceptor can both be donor can be A and the acceptor can be A, but we can also have a situation where the donor is A and the acceptor is B, or where the donor is B and the acceptor is A. And that's going to lead to 4 possible alkoxides. And when those alkoxides are rotated, hydroxy 2,2-dimethyl-pentanal. And here we have hydroxy 2,2,4-trimethyl. And if it was this messy to write it out, you can imagine how messy it would be actually getting all four of those products and then having to try to fish them apart. They're not very different. They're not going to have very different characteristics in terms of ability to separate them by boiling point or separate them by properties on chromatography columns. The fact that there are four possible combinations of donor and acceptor yielding four possible products makes this synthetically completely useless. So when would it be useful? Well, you'll notice that two of these products have no additional alpha hydrogen. The 2-methyl propanal only had one alpha hydrogen. So it can't go further. There's no way to eliminate water across the alpha and beta hydrogen on these two products and go to the alpha beta unsaturated carbonyl compound. Whereas with the other two products, because there's an additional alpha hydrogen here, it would be possible to remove that and proceed further. So it looks like there's going to be a mixture of four possible products, but if we heat it up, there really would only be a mixture of two possible products. And keeping in mind that it's difficult to isolate the aldol in the first place, especially if the significance there hinders, as there is in that material where there's no more alpha hydrogen, these are terminal. No further reaction is possible. In the other two cases, it would be possible to remove the alpha hydrogen still present, liberating enolate, step 4. Hydroxide. Generate alpha beta unsaturated carbonyl. And again, I'm drawing you guys. We can do the same thing for the other one. Presence of an additional methyl group over here, away from the carbonyl compound, is not going to have any effect on steps 4 and 5. Certainly remove that on the relay. Generate a second alpha beta unsaturated carbonyl compound. These differ only whether there's an ethyl group or an isopropyl group attached. So this is now a pentanal. This would be 2,4-dimethyl methyl, E2-methyl. But still, that's not that synthetically useful because we have to separate these two molecules which differ only by the presence of the methyl group and therefore not likely in polarity and probably relatively small difference in weight. So when is the cross-aldol condensation synthetically useful? In order to make it synthetically useful, what we need is we need to reduce the number of possible donor-acceptor combinations from 4 to 1. We can reduce the number of possible donor-acceptor combinations from 4 to 2 by choosing an aldehyde as the acceptor that has no alpha hydrogens. And as the other aldehyde, one that has the alpha hydrogens. So how do we make sure that this only acts as the donor? So we have this one donor acceptor possibility. Well, the answer is to put the non-enolizable aldehyde in solution with base, and then add the enolizable slowly. That way, we make it far more likely that the enolizable aldehyde is going to come into contact with hydroxide than it is to come into contact with its own enolate. Concentration of the acceptor is kept high, while the concentration of the donor is kept low. And we've seen this kind of concept before, where we were using the order of addition to control whether or not we got multiple alkylation in the case of enolate alkylation. So we're going to have our enolizable aldehyde added slowly to this mixture. And then we hope that that enolate is going to react immediately with the acceptor. non-utilizable carbonyl compound at base. So step 4. Remove the alpha H again. Solid wedge anymore because this is now a planar speaking where it has carbon. And step 5. Also hydroxide. Here's the alpha beta unsaturated carbonyl compound. So the final product, the alpha beta unsaturated compound, will be the only alpha beta unsaturated carbonyl compound form. You can avoid having it react with itself by dripping it in slowly, so that it's much more likely after it forms its enolate to run into benzaldehyde. To run into another molecule of propanol. Synthetically, this is quite useful. So the cross-aldol condensation is synthetically useful when only one carbonyl and it's synthetically most useful when it has 2 alpha hydrogens. Because if it only has 1 alpha hydrogen, which this is a secondary carbon, then steps 4 and step 5 are not possible because there's not a second hydrogen here. And usually the reverse reaction will occur and you'll not get a good deal of product. So we want 1 primary and 1 tertiary non-phenolizable. Any benzaldehyde can only ever act as an acceptor. So benzaldehydes are very commonly used in cross-aldol condensations, and in fact will be used for your cross-aldol condensation. I've got 2 aldehydes here, but this could have been a ketone. If this had been a ketone, we would also have seen a successful cross-aldol condensation. The catch if it's a ketone is that one side should be tertiary, so that you only have enolizable hydrogens on one side of the ketone, and thus you'll only form 1 enolate. For synthetic utility, we need the number of donor-acceptor combinations to be just 1. 1 donor,